Welcome back, guys. We're gonna start here with our balancing of another type of reaction to finish out our balancing of equations lecture number 6. And this is gonna be for nuclear reactions. So these are a little bit different than what we've been doing before, and we'll talk about those differences first. First, we have to talk about the fact that all elements having an atomic number greater than 83 are radioactive in nature. So they emit particles or electromagnetic radiation spontaneously. It's called radioactive decay. Nuclear transmutations are also things that we can do. So we can take a particular atom and we can bombard it with nuclear particles or with other particles. So anything that we can think of, and we'll talk about those particles in just a minute, to get it to try and do nuclear chemistry. All right, so we do that from time to time. And when we talk about chemical reactions and nuclear reactions, they are not the same thing, right? So we have different things that we're talking about. Chemical reactions, we have atoms that are rearranged by the breaking and forming of chemical bonds. Only electrons in atomic or molecular orbitals are involved in the breaking and forming of bonds. Reactions are accompanied by absorption or release of relatively small amounts of energy. And the rates of those reactions, which you'll talk about in detail in 111, are influenced by temperature, pressure, concentration, and catalysis. Nuclear reactions, on the other hand, elements or isotopes of the same elements are converted from one to another. Protons, neutrons, electrons, and other elementary particles may be involved. Reactions are accompanied by absorption and release of tremendous amounts of energy. And the rates of those reactions normally are not affected by anything that we normally see, not temperature, not pressure, not catalysis. Okay, so you should be able to look at a reaction and see if it's a chemical or a nuclear reaction. That is an expectation that we will have, is that you can identify if it's chemical or nuclear. Okay. Now, when we talk about elementary particles, we're talking about anything that appears on this slide. Now, is this going to be available to you? No. So this is not on the test. Now, does that mean you need to memorize it? Well, technically, yes. If you want to be able to answer these questions appropriately, yes, you will need to memorize this. Is it that prevalent? No, not really. We asked a couple of questions on the first test. They involved like, hey, here are the words, write this out and balance this equation. Which one of these is this kind of particle? There'll be some of these on the final as well. So there is that. Now, it's up to you. If you want those points or you don't. To me, those seem like easy points. To memorize these particles and get those points seems fairly easy. So I always recommend it, but that is entirely up to you. Now remember that a nuclide is an atom characterized by a certain atomic number and a certain mass number. So remember, we have our A, Z, N, where A is the mass number. So that's the number of protons plus neutrons. That's equal to A. Z is the number of protons. And not N, that is not what I meant. This is an X, and X is the atomic symbol. And that atomic symbol is determined by the number of protons that that thing has. Okay, so don't forget about that. Now, we can talk about a number of these different things, and I'm going to talk about the ones that we've talked about already first. So I'm going to skip a couple of these. We're going to go sort of out of order and in crazy order, so it's going to seem strange. We can talk about our neutrons. Those are particles that have no charge. They're roughly the size of one atomic mass unit, and they're symbolized by 1, 0, N. Okay, we've talked about those before. So they're half the mass of a nucleus. It's typically what we talk about. We can talk about a proton, which is a 11H or 11P. Okay, so that's what we look at when we talk about a hydrogen nucleus. Okay, so it's a nuclei of a hydrogen atom. It is symbolized by a plus. Okay, so we have that as a plus. It's roughly the size of 1 AMU, so about the same size. Okay, we have our positrons. Now, positrons are very, very tiny. They have a positive charge. They are actually electrons with a positive charge. So they're the same size as an electron, but they are positively charged. We symbolize them by saying either 0, positive 1e, or 0 plus 1 beta. Okay, so that's how we talk about our positrons. So tiny little guys, very little mass, but a plus 1 charge. When we talk about beta particles, that's a 0, negative 1e, or a 0, negative 1 beta. Those are high energy electrons, so they're negative, okay? They're just high energy electrons. So they often have a lot more, they can move a lot faster, is typically what we see. Okay, so that's a beta particle. We also have alpha particles. So we talk about these as alphas. They often get symbolized as an alpha, okay? Alpha particles are 4,2He, so that's a helium nucleus. We can also talk about them as 4,2 alpha, either one of those works. So there's 2 neutrons and 2 protons in here, so it's an 4,2He. Okay, and this last one, the one that we haven't talked about. So if any of you have watched the Marvel Cinematic Universe, you may be familiar with the fact that Bruce Banner was hit by a bunch of gamma rays and he turned into the Hulk. Well, these are those gamma rays. Okay, they're high energy particles. They're very short wavelengths, so it's very easy for them to penetrate us. Okay, but they're listed as gamma, so that is actually drawn like this. So that's a gamma. Now they're very high in energy, but they don't bring any mass to this. So when we use them as part of our balanced equation, we don't really have to do much with them except show that they're there. Okay, so they're not part of an actual balancing of that equation, but they are present because of the energy that they bring. Okay, so very high energy in our electromagnetic creation. Sorry about that. So these are the particles that we're going to be talking about when we talk about balancing these equations. And I can't get this to do this. So these are the ones that we'll be dealing with. Okay? So let's take a look at what this can look like. All right. So we're going to talk about some examples. So the goal here is to balance them and what are the unknowns, because we're typically going to do it in that fashion. So an unknown particle reacts with a proton to give magnesium 25 and an alpha. So I know that I'm going to get something giving me magnesium 25, which means that I have 25 Mg. Mg is atomic number. Pull this over so we can see that. So Mg is atomic number 12, so he's going to come down here. 12 Mg, and that 25 is the mass number. And an alpha plus an alpha. So 4, 2 alpha or 4, 2 He. Either one of those works. Now, that unknown particle, which has this mass number, our Z and our X, reacts with a proton. So 1, 1p. Okay. So I know one of my reactants. I need to figure out what that other reactant is. Okay. So that's what I'm trying to do, is figure out how I'm going to balance this thing. Well, I needed to have some kind of example to set that up. So I've now set this up in this way. What happens when we do this is we've got a bunch of stuff in this top line row and a bunch of stuff in the bottom line row. And we can't lose any of that mass, right? So A plus 1 is equal to 25 plus 4. So A plus 1 is equal to 25 plus 4. We also know that Z plus 1 is equal to 12 plus 2. Now, these are not related to each other, i.e., they're not equal to each other, but they have to be equal to, the two sides have to be equal to each other. So what I can do is I can do the math that I get from this. So 25 plus 4 is 29. I can then subtract the 1, and that means that A is 28. Okay? So this is 28 right here. So 12 plus 2 is 14. I can subtract the 1 that's here, that's 13. And if it's 13, then I'm looking right here. Number 13 is Al. And so that unknown particle right there is 2813 Al. And that's what I'm doing. Is just figuring out what that other number needs to be to make that true. That's it. Okay. So this is mostly about interpreting what else I've been told. So magnesium 25, again, that 25 after magnesium tells me the mass number for magnesium. Magnesium, again, is going to have that lower number be its atomic number. And then an alpha is a 4,2 alpha. And a proton is a 1,1p. And again, those guys came from this chart. So my proton was a 11H, where I listed as a 11P. And my alpha particle, I listed as 4,2 alpha, or I could have done it as a 4,2 He. Okay? So that's all I did, was to sub those things in and then solve for the one that I didn't know. So remembering those particles can be a pain, sure, but these are actually really easy as far as the balancing part goes. Okay? So 2813x and x is 13. Now I have another unknown particle, so an AZX, and it reacts with a beta particle. Now beta 0, -1b, and that gives me a proton. Oh, no, it says a polonium 214. Sorry, I misread it. Polonium 214. Well, polonium is this guy right here. So he's PO, and that's 84. And his mass number there is 214. And 2 alphas. So I have 2, 4, 2, HE. Okay. So that is my balancing. All right. So now I can look at this, and again, we're going through the exact same thing we did before. A plus 0 equals 214 plus 2 times 4. And if I look at that math, 214 plus 8. And I really suck at math, so forgive me for having to do this, but 214 plus 2 times 4, which is 8, gives me 222. I subtract the 0, and so A equals 2, 2, 2. I can do the bottom part. So I have my Z minus 1, because it's a -1 that's right there, is equal to 84 plus 2 times 2. So 84 plus 2 times 2. And then I need to get that -1 to the other side, so I subtract the -1. And that gets me 89. So Z is equal to 89. Because again, when I move all of this over, it's 84 plus 4 plus 1. Because when I subtract the negative, I end up with adding 1 to it. So that's 89. 89, looking at my table, is going to be AC. Okay. I must have made a mistake going and did this. Because I'm looking at the numbers that I wrote down here. And I definitely have 2 times 2, and I have 4, 2, so that's a helium, and 2 of them. But then I have a 0, -1, which is a beta, definitely. But I don't multiply it by here, by 2 here, and I do multiply it by 2 here. But I subtract it there, and I shouldn't be subtracting it there. I should be adding it because I would be pulling it over. And so rather than subtracting it, I should be adding it. If it was a 2, if it was supposed to be a 2, which I didn't write here because I didn't think that there was a 2 out in front of it. So I'm going to cross this out. That part looks fine. And again, we're going to go with what I've written here because it makes sense to do that. So again, so 84 plus the 4 from having 2 of the alphas, which gives me the 88. And then since I have a -1 here, when I subtract it on both sides, that gives me an 89. So when I get that 89, that's an actinium. So actinium 89. And of course, if it's an 89, my top number is 2. That's a 2, 2, 2, 8, C. Okay? I apologize for that, but again, I was inconsistent in what I did, so I didn't multiply this one, but I did multiply it here. So apparently there should have been a 2 out in front of it, but I didn't multiply the 0. So since I didn't look at that appropriately, I'm just going to leave it the way I did it. Okay? So questions, comments, problems on what I did. And if that does confuse you, please let me know. Okay? So that's that one. So let's try a few more. NASA uses the alpha decay of plutonium-238 as a heat source on the spacecraft. Write the balanced equation for this. So what's an alpha particle again? So alpha was the 4, 2He. Plutonium-238. So if I go find my plutonium, this is polonium. Where's my plutonium? Darn good question. Oh, that's platinum. He's not that one. And half the battle is trying to find them on the table. See if I can find them on my exam handouts. Ah, 94 PU. 94 PU. And again, 238 comes up here. Why I couldn't find him on the table beats me. I just couldn't. I was looking right at him and I couldn't see him. 94. He's down here. So right there. Okay. Plutonium is atomic number 94. And it says that right there, and I still couldn't find him. Yay. All right. So uses the alpha decay of plutonium-238 as a heat source. So what that means is that I've got my 2, 3, 8, 94 Pu going to give me that 42He and some other thing. All right, because we're using that alpha, that alpha particle to give me the heat. Okay. So I take my 238 minus the 4, and that gives me 234. And I take that 94 minus the 2 from here, and that gives me 92. And so I look at my 92, and that's uranium. Uranium is U, so we put that right there. Okay. So again, here we're looking for where to think, what are those particles and where do they go? So that 238.94 Pu is my starting material. That alpha decay means that it's a product. And then we need to know what that other product is. Okay? So questions, comments, problems on that one? All right. I want to predict the nuclear equation for each type of decay. I have beta decay in BK249. BK249. Where is BK? BK is 97. He's right there. So I have my BK 97 to 49. He's going to decay to give me a beta, 0, -1 beta, and something else. That's going to be a 249 because we've made no change in that mass number. 97, and of course we need to have that -1 from there, so that means we have 98 added to that. So 98, that next one over is CF. Okay, so that's the one we're talking about there. Positron emission in oxygen 15. So oxygen being number 8, he's right here. So O8 and his mass number is 15. We're getting a positron emission, so 0, -1 beta, because that's one of the ways I can symbolize him, plus 15, because there's no change in the mass number, -1 beta. Wait, hold on. Oh, no, my positron is not -1 beta. It's a +1 beta. Yeah. That guy. So if that's the case, then this needs to be a 7. And 7 is nitrogen. Okay. So positron should be positive, not negative. And then electron capture in iodine 111. So iodine 111 is iodine. Iodine is 53. So iodine here, 53 there, and 111 here. We have electron capture. That means I'm going to have a 0, -1 E on this side. And then I want to know what that product is. Again, 111 because I haven't changed the mass number. And 53 plus that electron is going to give me 52. So that 52 is TE. So a couple of things that I've noticed here. Beta decay, the beta is a product. Positron emission, that positron is a product. Electron capture, the electron is a reactant. Okay, so some of those wordings and terminologies are things that you'll need to be aware of when you're trying to balance these equations. Okay? All right. Well, that is the end of our balancing. So hopefully that was fun. And if it wasn't, then let me know. I'm going to go ahead and stop sharing. And I will stop the recording here, and I will talk to you soon.